Quantum computers won't make your laptop faster. They won't speed up your phone or make Netflix load instantly, but they could break the internet. That's the paradox. A machine that seems infinitely powerful in theory, but in practice, it's only extraordinary for a handful of very specific problems. And that narrow focus could still transform everything, from global security to the future of medicine. When most people hear quantum computer, they picture something like this: magical supermachine trying all solutions at once across parallel universes, spitting out instant answers to anything. But here's the question. If that were true, why aren't we already running the world on quantum chips? Why do experts keep saying we're decades away? And why do computer scientists insist that quantum computers don't make everything faster? To understand the paradox, you need the three pillars of quantum computation. First, superposition. A qubit can be 0 and 1 at the same time, represented as probabilities. Second, interference. Quantum states overlap like waves. Some amplify, others cancel out, letting the computer weed out wrong answers. Third, entanglement. Particles become linked, so measuring one instantly influences the other. This correlation can link information across the system. These three principles enable specialized algorithms. Shor's algorithm, which can factor large numbers exponentially faster than classical computers. It is a direct threat to RSA and elliptic curve cryptography. Grover's algorithm, which accelerates search tasks but only quadratically, meaning it's useful but not magical. And then there are demonstrations like Google's 2019 random circuit sampling experiment, which showed a quantum processor solving a task in minutes that would take a classical supercomputer thousands of years. Sounds unstoppable, right? But here comes the twist. Quantum computing isn't a universal speed button. It's a surgical tool. In complexity theory, there's a class called BQP, the set of problems quantum computers can solve efficiently. But it's not known to include NP-complete problems like the traveling salesman or complex scheduling. In other words, quantum computers can obliterate some problems, factoring, chemistry, cryptography, but they're no better than classical systems for many others. That's the paradox. Extraordinary power on narrow fronts, but no advantage for the vast majority of computing tasks. And even for those special problems, today's hardware isn't there yet. We live in the NISQ era, noisy, intermediate-scale quantum. Devices with dozens or hundreds of qubits that are powerful but fragile. Every calculation is haunted by noise and errors. To correct them, you need massive overhead. Surface code error correction requires hundreds or even thousands of physical qubits just to make one logical qubit. So when companies announce hundreds of qubits, remember, that's not the same as hundreds of useful qubits. Fault-tolerant systems may need millions. That's why IBM, Google, IonQ, and others are racing on hardware. Progress is steady, but we're still far from building the machines capable of running those world-changing algorithms. So why does this matter? Because even in its limited form, quantum computing reshapes the world. First, security. Shor's algorithm can, in principle, break RSA and ECC, the backbone of Internet encryption. That's why NIST has already standardized new post-quantum cryptography algorithms like Kyber, Dilithium, and Sphinx Plus. Governments and companies need to migrate now to protect data that must remain secure for decades. Second, science and industry. Richard Feynman once said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum." That's where quantum shines, simulating molecules, designing catalysts, developing new battery chemistries. These aren't just academic exercises, they're billion-dollar breakthroughs. Third, energy and climate. Imagine modeling fusion reactions, optimizing power grids, or finding materials that can capture carbon at scale. These are problems beyond classical high-performance computing, but they may be within quantum's reach. So here's the truth. Quantum computers won't make your daily life faster. They won't replace your laptop. but they will crack problems that no classical computer could touch. They will unlock the chemistry of life, the physics of energy, and the mathematics of security. That's why governments call it the quantum race, not for universal speed, but for the few breakthroughs that could tilt the balance of power, science, and industry. The paradox of quantum computing is that it's almost useless for most tasks, and yet absolutely revolutionary for a few. That narrow advantage is enough to reshape entire industries and maybe even geopolitics. So the next time you hear the hype that quantum will make everything faster, remember, it's not about speed, it's about possibility. Because the future isn't built by doing the easy things quicker. It's built by making the impossible possible. If this video helped you and you want to watch more videos like this, hit the like button and subscribe to my channel.